So now that we know what an algorithm is, and the notion of growth of functions like big O and big omega and theta, we want to put these two together and talk about the complexity of algorithms. In other words, we want to talk about getting an estimate of the running time of an algorithm or the amount of memory that an algorithm takes using this notion of growth of functions. We are not now talking about if I implement the algorithm in Java and run it on this computer, how many seconds it takes, or if I take the algorithm implemented in Python and run it on that cluster, how long it takes. We are talking about, here is an algorithm given in pseudocode. Here are details how we are going to implement it. Not in the specific programming language, but here are the data structures we are going to use and so on. What is a rough estimate of the number of steps it's going to take as a function of the input size, so that we have an idea of how good or bad the algorithm is before we even implement it. And this is what I'm going to be talking about here. So the first point is, when we are asked to come up with an algorithm for a problem, of course we are interested in coming up with a correct algorithm. But coming up with a correct algorithm, there could be multiple correct algorithms. And our interest is in choosing the most efficient among all of them. Okay, so if I ask students to write an algorithm for a problem and I get 21 different algorithms or 59 different algorithms or whatever it is, I'm gonna, of course, go and look at, okay, which one of them is the most efficient? Which one is gonna run fastest? And which one is going to consume the least amount of memory? Let me take that. When we talk about efficiency of an algorithm, we usually talk about time, but very often also we think about space, right? So especially in the era of big data, if the algorithm is running on a matrix and the matrix has million rows and million columns, well, forget about the running time. How do we even load this thing in the memory, right? So a million by million matrix, the amount of space is a problem there. But usually when we talk about space of an algorithm, is that how much space it uses in addition to the input size, okay? So I feed the algorithm some input and starts using space for doing the calculation. How much space it's going to use? The same thing with amount of time. We usually, not always, but usually we are not concerned with the amount of time it takes to read the input. But once it's read the input, how many steps is going to take to finish computation on the input? I put there in parentheses or in square brackets that in some cases, we might opt for slightly slower algorithm at the expense of ease of implementation, right? So if I have algorithm A is more efficient than algorithm B, but algorithm A is a nightmare to implement because of all sorts of fancy data structures and so on, sometimes we might opt for algorithm B. When we talk about the running time or amount of memory that an algorithm takes, I want you to focus on this specific point that's all in the title of this slide. It is all a function of the size of the input, not the value of the input. Not the value of the input, but the size of the input. How many bits, in some sense, are being used to describe the input? Okay, this is what we mean by the input size. Okay, so when we talk about the running time of an algorithm and we say this algorithm takes O of n squared, we are saying that if the input is of size n, the size of the input is n, then this algorithm is going to take on the order of n squared steps, or is going to take a number of steps that's bounded from above by n squared. Okay, so for example, an algorithm that sorts a list, the input size is the number of elements in the list. If you write an algorithm that takes as input, an array of size n and does linear search, the input size is n. If you are multiplying two matrices, the input size is the number of entries in these matrices. If your algorithm computes the cardinality of a set or is performing computation on a set, the number of elements in the set is the input size. Okay. In some cases, more than one parameter is needed to capture the input size. So one of these examples is, for example, if I want to compute the intersection or union of two sets, then if the two sets are not of the same size, it's usually important to have two parameters to describe the sizes of the two sets. If I'm multiplying two matrices, the two matrices do not need to have the same dimension. The first one can be m by k, the second one is k by n. m and n could vary significantly, in which case I need to describe the input size of two matrices. One is m by k and one is k by n. Then there are three parameters to describe the input size. It's m, k, and n. Now, in some algorithms, it gets trickier than that, but we have a class of algorithms, for example, that work on integers, on large numbers. So, for example, there are algorithms in number theory that test primality of a number. So the algorithm takes as input a number, and it answers, yes, it is prime, no, it is not prime. Such algorithms are usually invoked or used in the area of cryptography and security. And when these algorithms are used, they are usually run on very, very large integers that have tons of digits in them. Nobody wants to devise a security protocol and is trying to determine the primality of the number 75, right? This is very easy to solve. In such a case, the input size, the algorithm is running on one number, on p, right? But the input size is not 1. We cannot say the input size is 1 because it's running on one number. The problem here is that the number can be very large to describe. So in this case, the input size is the number of bits that are needed to describe p. So if p is a number, given that computers, we work with binary representation of numbers, zeros and ones, so how many bits are needed to describe a number, the number whose value is p? It's log 2 of p. So in this case, the size of the input is the number of bits in that input, which again can be described as the log of p to the base 2. Okay, but this is relevant usually in the case of these kind of algorithms that are working on integers. But searching algorithms for multiplying matrices, algorithms that run on graphs, on sets, on strings, and so on, the input size is usually clear from the context. Okay, so if we are running it on a string, we want to search something in a string, the length of the string is the input. If we are searching in an array, the number of elements in the array is the input size, and so on. How do we measure running time? Again, it's not in terms of seconds, it's not in terms of minutes, and so on, because then that's all a function of the computer, specifics of the computer we are dealing with. We usually focus on basic operations that the algorithm is doing. So an algorithm that is searching, for example, an algorithm that is searching in an array, usually the basic operation it's doing, it's comparing the element we are searching for against the elements in the array. So these equality tests are basically what the algorithm is doing. If you are sorting algorithm, usually the basic operations they do are comparing elements, right? So we want to move the smaller elements to the beginning of array, the larger elements to the end of the array. In this case, the basic operations are comparisons. So basic operations are, comparisons, addition, multiplication, and so on, that we usually see in algorithms. The complexity analysis framework ignores multiplicative and additive constants and just focuses on the order of growth. And this is where the order of growth of function comes into the picture. That when we are looking at the running time of an algorithm, we don't say it takes 7n squared plus 13. We say it takes on the order of n squared. 7n squared plus 13, we can say it takes on the order of n squared, because when I say 7n squared plus 13, I can drop these multiplicative constants and additive constants, and I say it's n squared, okay? Same thing, if someone says the algorithm take 5 times n factorial, really 5 is not going to make any difference. N factorial is already a disastrous function, so we say this is just n factorial. Now, please be careful. I am saying multiplicative and additive. I cannot take n to the 2 times 3 and say, well, this is multiplicative, let me drop this 3. No, we cannot. This is not multiplicative constant now, okay? So this is what's achieved by this big O notation and omega and so on. So when we analyze running time, we don't want to get into the details of, this addition takes 3 steps versus 2 steps. Because these are constants. 2 and 3 are constants. It doesn't matter, we can drop that. Right? This is the whole the whole idea behind using growth of functions rather than counting exactly the numbers. And we will illustrate that on some algorithms. Okay. One thing before we deal with analyze the running time of some algorithms, I want to make a distinction here that's very important distinction between the complexity of a problem, the complexity of an algorithm. Complexity of a problem is not a statement about a specific algorithm. It is a statement about how easy or hard the problem is, which basically means that if I say problem X cannot be solved in less than n log n, if I say problem X cannot be solved in less than n log n, I am saying you cannot find an algorithm whose running time is better than n log n. If I am talking about the running time of an algorithm and say this algorithm takes n log n, this doesn't mean that there isn't another algorithm that does exactly the same thing but in n steps, for example. Okay, so the complexity of an algorithm, I'm analyzing the algorithms, the specific algorithms I'm dealing with. Complexity of a problem is a general statement about the problem, not about a specific algorithm. So here's one famous example of when we talk about complexity of a problem. So when we try to sort numbers, if you give me n numbers and say sort them from an increasing order from smallest to largest, there is a very important and central mathematical result that says that you cannot sort in numbers. You cannot sort in numbers in less than n log n, as long as your algorithm is doing comparisons, comparing elements to swap them and to shift them around in the array. So this is a statement about the sorting problem, not a statement about an algorithm, because there are algorithms that take n log n for sorting. There are algorithms that take n squared for sorting. In fact, one can write a terrible sorting algorithm that's correct and take n factorial. So the statement that the sorting problem is solvable on the order of n log n, it means that there exists an algorithm that can do it in n log n. It doesn't mean that every algorithm for the sorting problem takes n log n. But if I analyze the specific running time of an algorithm, of a specific algorithm, like merge sort, I am talking about merge sort takes n log n. As another example that's also very famous, but outside the scope of what we are talking about here, we talk about problems being NP complete. This is you can, if you're curious about it at this point, you can search this term. But in general, what this means that we don't know of any efficient algorithm for the problem. We don't know of any algorithm whose running time is n squared or n cubed or anything like that. The best we usually have for these problems is on the order of 2 to the n or n factorial and so on. When we say the problem is NP complete, we are saying that we don't know of an efficient algorithm for this problem. But we could have algorithms that take 2 to the n. We could have algorithms that take n factorial. We could have algorithms that take 2 to the n and so on. One other word here is about under what condition are we analyzing the running time. So when I want to analyze the running time, okay, we have agreed that we want to use growth of functions. We don't want to get to the exact number, but we want to say it is on the order of n squared and so on. The second point, we said that it's all a function of the input size. So I determined the input size is n, and I decided I'm going to use the big O notation. And now I want to analyze the running time. The running time is under what condition? And there are 3 conditions that we usually analyze the running time under: the worst, best, and average cases. In the worst case, we are saying that of all inputs of size n, which input results in the largest number of operations that the algorithm would take. And that number of operations is the running time of the algorithm in the worst case. Okay? In the best case, of all inputs of size n, what is the smallest possible number of operations that the algorithm would take on an input of size n? Okay, so there could be some, even though the problem is hard, there could be some very easy cases of that problem of size n. That very easy to get the answer. What is the running time in such a case? In worst case, I look at the problem, there are some very, very hard cases of size n. For those, how long does it take? This is the worst case. Average, it's the expected number on average over all possible inputs of size n. what's the number of steps that the algorithm would take. Again, these cases are defined for a given input of size n, not for changing the input size, okay? So if I am looking at linear search, nobody can say that the best case corresponds to the array being empty. That's not an input of size n. I am asking you for linear search, when you look at the input of size n, what is the best case? For what arrays of size n does linear search result in the fewest possible number of operations? For linear search, what is the worst possible input in terms of forcing it to take the largest number of steps, and so on. The same thing with average, okay? Best case analysis of an algorithm is usually uninformative about the algorithm. It just tells us that there are some easy cases, or not easy, but there are some cases where the algorithm can take this many steps. So in other words, the best case puts a lower bound on the number of steps that the algorithm takes, but that lower bound can be very, very far from what we see in practice. So for example, if I'm doing linear search and I say in the best case it takes 1 step, well, what I'm saying here is that the running time of this algorithm is bounded from below. At least it has to do one operation. But in practice, when I am doing search, I might not see any such examples, and most of the time it could take on the order of n steps. The average case is actually the most informative of them, but it's usually the hardest to establish, and it usually requires probability theory because we need to use the notion of expectation. So we introduce random variables that correspond to the number of steps, and we compute the expected value of these random variables. Maybe the most commonly used one is the worst case analysis, where it's easier than the average case. It's much more informative than the best case. And we are saying here, in the worst case, what's the running time of this algorithm? Just in case we hit these bad cases, how long does it take this algorithm to finish? Okay, so when we talk about running times of algorithms, usually we like things all the way from here and up. Okay, so these ones are fine. These are good in some sense. These are terrible here. These are bad. Okay, so an algorithm, when we talk about an algorithm having constant complexity, we are saying it's taking theta of 1. This is an algorithm that no matter what input size you have, it takes a constant number of steps. It's not easy to think of many useful algorithms whose running time is O of 1. Like an algorithm that takes as input 2 numbers and returns the sum, for 2 small numbers, the running time is constant, right? But again, this is not many useful algorithms are theta of 1. Logarithmic complexity, this is O of log n. There are some famous algorithms that take log n. This is a very good running time because it grows very slowly with the input size. For example, binary search, how we search for an element in a list in a specific way when the list is sorted, can be done in log n. Linear complexity is when the running time of the algorithm in the worst case, for example, is theta of n. Linearithmic complexity is when we have n log n. Polynomial complexity when we have theta of polynomial, n squared, n cubed, n to the fifth, into something that's constant. Exponential, again, is when we have 2 to the n, 3 to the n, and so on. Factorial, when we have n factorial. Again, n 2 to the n, 3 to the n, and so on are bad. N factorial is bad. And here's an illustration what I mean by bad. So imagine that we have the input size n, and imagine that we have algorithms, we are running the same algorithm of input size n, but we are increasing n from 10 to 100 to 1000, so we are increasing it by an order of magnitude. Let's assume that 1-bit operation takes 10 to the minus 11 seconds. So this is a reasonable estimate for today's computers. Look what happens here. So imagine that we have 6 algorithms. So one of them takes log of n. One algorithm takes n, is linear. One of them takes n log n. One takes polynomial, quadratic in this case, n squared, 1 2 to the n, 1 n factorial. So look what's going to happen here. If you run these algorithms, 6 algorithms on an input of size 10, all of them are going to finish in fractions of a second. if you look at the first row there, all of them will finish in a fraction of a second here, right? So all of them in a fraction of a second. Look at what happens when we go from a list of size 10, so from 10 numbers to 100 numbers. The first 4 finish in fraction of a second. These finish in fraction of a second. The exponential one takes on the order of 10 to the 11 years to finish. The polynomial, we cannot even finish in less than 10 to the 100 years. So this shows you how bad these 2 to the n and n factorial are in practice, because we usually are dealing with, when we talk about analyzing data, it's very rare that we even talk about n equal 10. We are talking about millions, 10, n equal million, and so on. These two algorithms, 2 to the n and n factorial, are just infeasible to run in practice. So this is a very important picture to keep in mind here, that when we talk about algorithms, we want the algorithm to be correct, but if the algorithm takes on the order of 2 to the n or n factorial, that's not a practical algorithm. This is not an algorithm that's worth implementing and running. Of course, unless the input is always of size 2 or 3 or 4 or 5. But it's very rare that we have problem of interest in practice and the input size is 5 or 6 or 7. Usually the n is very large. And this tool of analyzing the efficiency of algorithm using the growth of function as a notation, this is a very powerful tool that allows us to reason about how an algorithm takes before we bother to implement it. And if we reason about it and it's 2 to the n or n factorial, and our analysis is careful, not the loosest analysis possible, then maybe we don't need to implement it. So let's look at a couple of algorithms here to analyze their running time. Linear search is one of them. We have seen this. So what is the input size in this case? The input size in this case is n. I don't need to say n plus 1 because of x. N and n plus 1 are the same for our purposes here. So if I look at this, the input size is n. And I want to analyze this running time. Let's look at first the best case. So the best case, what is the best case of this algorithm? So first, what is the best case that corresponds to linear search? I am searching for an element x in an array of size n. The best case is when I check x against the very first element in A and I find it there. So what happens in that case? What happens is that we end up assigning I equals 0. Then we end up checking this condition here and the condition evaluates to true. And then we check this and it evaluates to false and we come here. So what we really do are really 4 things. We assign I equals 0. We check this condition and it turns out to be false. Then we check this condition, it turns out to be false, and we return I. In the best case, if you give this algorithm an input of size n, even if n is trillion elements in the list, this algorithm is going to do just these 4 lines there, 4 operations in a sense. So 4 is O of 1. So in the best case, this algorithm takes O of 1 operation. It's a constant. In other words, in the best case, no matter what n is, this algorithm takes a constant number of operations. What about the best case? The worst case. So in the worst case, when does linear search have the worst case? I am looking for an element in an array. The worst case is when the element is not in the array, because that forces the algorithm to go through the entire array element by element, checking everything, and it doesn't find. So of all the inputs of size n, of all arrays of size n, the arrays that don't have x correspond to the worst case. In this case, what happens? Line 1, this line here, is O of 1 operations, is in the order of 1 operation. This loop here on lines 2 and 3, we check for I equals 0, the condition is true. We check for the condition I equal 1, it's true, 3, 4, 5, all the way to n. So this takes on the order of n here. So lines 2 and 3, in the worst case, when x is not in the array, lines 2 and 3 are going to perform some constant times n. This one here, whether it is true or false, in this case is going to be true, where I is greater than n. This is O of 1, because this is about constant number of operations, and this one here is O of 1. Now look at this, we have O of 1 and O of n and 1 and 1. If I drop the O, the letter O from there, so I'm talking about 1 plus n plus 1 plus 1. Remember that if I have a polynomial, it is O of n to the largest power there. So it's O of n. So in the worst case, this is O of n. Okay. I am not going to do the expected value for this algorithm because again it requires different tools for doing this. So this algorithm here for input size n, in the best case it will take O of 1. In the worst case it will take O of n. Let's look at this algorithm here, the complexity of matrix multiplication. We have A is a matrix of n by k, B is a matrix k by m. We are multiplying them. Well, in this case, if you look at this here, the worst case and the best case don't matter here, don't make a difference, because you have to do the multiplication in the same way. And the input size here can be given in terms of n and k and m. Okay, so we can, for example, give the running time of this as a function of n and k and m. How long does line 1 take? It's looping from 0 to n minus 1. This is on the order of n steps. This one here is on the order of m. This one is on the order of 1. This one here is on the order of k. And this one here is just doing multiplication and addition and so on. This is on the order of 1. Okay? So, and this is on the order of 1. And here now I want to remind of tools that we looked at when we dealt with the growth of functions. So these two here are multiplied because the first line, the for on the for loop on line 4 is running and doing what's on line 5. So this is k times 1, so this is O of k. And these two here, these three, it's O of 1 plus O of k, it's O of k. Okay, so these ones here, this is O of k. But this O of k is being multiplied by a function that O of m. Remember that we have if we have two functions f of g, then f times g is O of f times g. So now these two are O of k times m, and these are multiplied by this function here, which is O of n times m times k. Plus 1 for the return, but that doesn't matter. So this algorithm takes on the order of n times k times m. And in this case, for this algorithm, it happens to be that best case, worst case, average case, it will always take O of n times k times m running time. Okay? If the matrices are n by n, so if both A and B are square matrices, are n by n, this is a cubic algorithm. It's O of n cubed. Okay. I'll just finish with a few words about algorithms and problems. I want to just say that, in practice, we have a class of problems that are in what we call intractable, that we don't have any efficient algorithms for them. We have two classes of problems that are defined in the theoretical computer science domain. One is called P and one is called NP. Usually, again, I'm not trying to be formal here, but class P is the set of tractable problems. These are problems for which we have polynomial time algorithms. So problems for which we have algorithms that take n squared or log n or n log n or n to the 50, these are all in class P. Problems for which we don't know of good algorithms at this point are not in P, okay, outside P. And we have a class called NP complete that consists of problems that for which we don't have good algorithms. We don't have algorithms whose running time is polynomial or better. But the one nice thing about them is that if we can solve one of them, we can solve all the other problems in this class. Whether P equals NP, this is literally $1 million question. It's still open after decades of research into this question. We still don't know if some of these problems in NP that are not NP, eventually we will find polynomial time algorithm for them or not. At this point, we know this. We know that P is a subset of NP. right? But the question is that there are lots of problems that are here, that are outside P but inside P. At this point, we don't know if these actually belong to P, if these two are going to collapse or not. Okay. Now, it can get even worse than P and NP complete and polynomial and factorial running time. In fact, there are problems for which we have no algorithm. Okay, so there are problems we don't have an algorithm. Forget about running time. There is no algorithm for them. So for example, if you write a computer program to do whatever, and I give it an input and I say, is your program going to halt? Is it going to terminate eventually on that input? This is a problem that in general have no solution. We cannot come up with an algorithm for it. If you are curious about this, you can search the halting problem and read about it. But this is a fundamental problem in the area of computability and the abilities or the capabilities of solving problems. Another problem is known as post-correspondence problem. Imagine you are given a list, two lists of n words each, and I'm saying, can you take these words and with repetition, can you take as many words as you want, concatenate them, and you get exactly the same word. So for example, if I give you the list of 4 words there, x1, x2, x3, x4, x1 is AB, the word AB, x2 is BB, AA, BA, and so on, and I give you 4 words of Y, I said, can you now take lists from X's and Y's and concatenate them to get the same words? The answer in this case is yes. So if you take and here's the solution. If you take x1, x3, x2, x4, x4, x3, what you get is A, B, and x3 is B, x2 is B, B, A, A, B, A, and x4 is B, B, x4 is B, B, and x3 is B. And now let's look at y1, y3, y2, y4, y4, and y3. What do we get? Take y1, it's A, y3, we get B, 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 and we take y2, it's A, and y4, it's AB, and y4 is AB, and y3 is B, 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 B. If you look at these two, they are the same word. And sometimes actually you don't have a solution. So if you try no matter how many times, you are not going to be able to form the same word from both of them. If I ask you this problem, if I go back to this problem, I say, I'm giving you 2 finite lists of words. Both of them are lists of size n. Can you take actually a sequence of these words from the x's and from the y's that when you concatenate, you form the same word? This is a problem that has no solution. Okay, so this is a problem that has no solution. So if we look at problems, a classification of problems in computer science, we really have the good ones are problems for which we have algorithms, and these algorithms are efficient. Take, linear time, quadratic time, logarithmic time, and so on. There are the bad problems, which are problems for which we have algorithms but not efficient at all. There are the ugly ones, again, the halting problem and post-correspondence problem and so on. For these ones, we don't even have an algorithm to solve them.